that cell before we move on to the next cell with the next lowest cost. So let's try to do that then. B in this case can supply 40 units. G, however, requires only 30 units. So we're going to try and maximize the flow from B to G, and we could supply 30 units. That will take care of the demand for G, so we could cross that out. B still, however, has 10 more units left that it can supply to any of the other points, so we cannot cross out the 40 units for B just yet. B still has 10 more units that can be allocated elsewhere. Moving on from the $0 cost to the next best cost that you see in this grid, we have a couple of cells here which have a cost of $3 associated with it. The cell C to E, or the cost of transportation per unit between C to E is $3, and the cost of transportation between C to F is also $3. If you have a situation like this where there's a tie between two options that you have, it's really up to you how you want to break the tie. You could arbitrarily break the tie using any procedure you want. Some procedures, of course, are better than others for breaking the tie. In my example that I'm showing to you, I'm actually just going to break the tie by taking the cell that is on the left or taking the cell that's above the other cell. So in this case, I have a tie between CE and CF, and I will arbitrarily just try to satisfy the flow from C to E before I do the flow from C to F. So in this case, C to E, if you look at that cell, then E has a requirement of 60. C can supply to a maximum of 75. So we will be able to satisfy all of the demand for E and supply 60 units from C directly. That will take care of the demand for E, so we could cross that out. The next cell that we have here is the $3 cell, again, from C to F. F requires 25 units. C, you've already supplied 60, so C only has 50 more units that can be allocated elsewhere. So we will try and supply the 15 from C to F, which will take care of, or which will exhaust the supply for supply point C. So C cannot supply any more units now. We've only satisfied the demand up to this point for E and G, and only 15 units for demand point F. F still requires 10 more units from somewhere else. Next up, after $3, there's a couple of cells which have a cost of $5 associated with it. And like I said, based on the tie-breaking rule that I'm using, I'm going to choose the cell that comes first from top to bottom, left to right. So I would like to use the cell from A to G. However, G does not require any more units. I've already satisfied the demand for G, so I don't need to do anything in that cell. The next cell with $5 cost is from C to D. D requires 50 units. C, however, cannot supply any more units. It's already exhausted its supply, so I can't do anything in that cell either. From $5, the next one up is the $6 cell over here from A to F. A can supply 50. F still requires 10 more units. So let's supply those 10 units from A to F. After supplying the 10 units from A to F, you've now satisfied the requirements for F. So you could cross that out. And now you can move on to the next cell after $6. So you have 3 cells now which have a cost of $8 associated with it. So you don't need to do anything in for these 2 cells from A to E or B to E, because E's requirements have already been satisfied. Similarly, you don't need to do anything from B to F because F's demand has already been satisfied as well. Move on from the $8 cost to the $9 cost that you have. From A to D, there's a $9 cost. From B to D, there's a $9 cost as well. So we're going to supply from A to D first. D requires 50 units. A, however, has already supplied 10 out of its total possible of 50, so it can now supply 40 to D. So we will do that, which will take care of the total supply that was possible out of A. So A is now exhausted all of its capacity. Next cell below is from B to D. B can supply 40. D still requires 10 because you've supplied 40 out of the 50. So let's supply those 10 out of B, which will now take care of the demand for demand point D as well. B in this case has also now supplied the total that was possible, 30 plus 10, and that was the total that was possible out of B to begin with. So we've now exhausted the total supply out of B as well. So now, again, we've crossed out all of our supply points and demand points. We've met the demand requirements and we've exhausted all our supply. And this is a solution that you get using the intuitive lowest cost method. Again, to find the total cost in this solution, we're going to multiply the flow times the cost. So 40 times 9 plus 10 times 6 plus 10 times 9 plus 30 times 0 plus 60 times 3 plus 15 times 3. Or in Excel, you could just do a sum product of the flows and costs, and that will give you $735, which is much less than what you saw in the previous scenario where our total cost was $1,205. So this does give you a better solution than the previous procedure. However, both of these solutions are feasible. They're not optimal. We don't know whether these are optimal or not, but they are feasible solutions. So that is the intuitive lowest cost method, and it does give you another option to choose for your decision variables. So the decision variables that we've changed in this case are the flows from the various supply points to the demand points. And by changing the values for these decision variables, we've come to two different solutions, and both of these are feasible solutions. So now that we've seen two different heuristic procedures to solve a transportation problem, we're ready to talk about the optimum solution. And for that, we're going to use linear programming to solve the transportation problem. Again, I've already defined linear programming for you, where we have different parts of the problem. So the objective function in the transportation problem is to minimize the cost that's associated with transportation, which is the sum of flow times cost between the various demand points and supply points. In terms of the constraints of a normal transportation problem, your supply from the various sources should not be exceeded from the maximum capacity of those supply points, which we just saw in the previous case. The demand at the various demand points or sinks should be met as well. That's your other constraint. The flows and costs should both be non-negative. The costs are typically given to you in the transportation problem, so those are considered to be the parameters of the problem. Flows are your decision variables, and that is what you're trying to work with and get different values for to find the optimum solution to the problem itself. These constraints, however, might need to be adjusted if our supply exceeds our demand or our demand exceeds our supply. So the greater than or equal to sign or the less than or equal to sign or the equality sign will need to be changed depending on the actual scenario itself. And I will show you a couple of more advanced examples in a bit for these unbalanced transportation problems where the supply and demand might be different. Also, in certain problems, there might be infeasible routes, so where you do not really have a route between a particular supply point and a demand point. In those situations, what you typically do is assign an arbitrarily large number as a transportation cost between those points. So if we are talking about costs in hundreds of dollars, you can assign a cost in tens of thousands of dollars between a supply point and a demand point, and that will take care of that route, and solver or any other optimization tool you're using will probably not use that route at all. In terms of formulating this problem, I will show you the formulation or express the formulation manually before we actually formulate this in Excel. The formulation, what we're trying to do is minimize the total shipment cost or minimize the total transportation costs from the origins to the destinations. The origins have a supply that's possible out of those points, and we denote that as S sub I. The destinations or the demand points each have a demand which we denote as D sub J. So I and J, again, are just indices that we're using for various supply points and demand points. The unit shipment cost from point I to point J is C sub ij. So C sub ij just simply shows you the cost of transportation from one supply point to another demand point. So this is what the mathematical expressions look like for your objective function. So your objective function here is to minimize the cost of transportation between supply and demand points. Cost is given as C, and the flow is given as X. So what we're saying here is for all I and J, multiply the flow times the cost from I to J, and take the sum of that over the entire transportation grid or the transportation graph. That's what you're trying to minimize. Again, it might look more complicated than it really is, but if you've understood what we were doing in our heuristic examples, this is exactly how we calculated our total cost of transportation. In terms of the constraints, again, if you look at the constraints that are given to you using various types of inequalities, what we're saying here is for each supply point or for each origin I, everything that's coming out of I should be lesser than or equal to the total possible supply for that supply point or for that origin. So in this case, what we're saying is for all J, starting from J equals 1 to J equals N, which are all of your demand points, everything that's coming out of I and going to these various demand points, the sum of that is lesser than or equal to the total supply out of that supply point. For each destination, which is your second constraint for your demand points, each of those destinations has a particular demand or requirement, which we denote as D sub J. So everything that's going into J, so from all of the I's into that particular demand point J, take the sum of all the flows into that demand point, and that should be equal to the demand for that demand point. Also, all of your flows, which are shown as X, are greater than or equal to 0 for all I and J. So for all of your supply and demand points, any flows in your solution should be greater than or equal to 0. So that is the non-negativity constraint that I spoke of before. So that is your formulation for a general transportation problem. Like I said, the inequalities might change a little bit, or there might be additional constraints depending on if we're talking about a more complex problem. So let's go back to our example, which I've shown you before. So this was the transportation grid that was given to you for that example. Again, 3 supply points A, B, and C, 4 demand points D, F, and G. You're given the constraints for the supply for each of the supply points. So A can supply to a maximum of 50, B can supply a maximum of 40, C can supply a maximum of 75, and you're given the constraints for the demand points. So requirements for D are 50, requirements at E are 60, at F are 25, and at G are 30. This again is an example of a balanced problem, so it's very easy to solve. I'll show you the manual formulation before I move on to the Excel spreadsheet formulation of this. In the formulation, I'm going to again use X sub ij as the flow from node I to node J. So X sub AD will show the flow from A to D. So let's look at what our objective function will look like. So this is our objective function. So the flow from A to D is X sub AD. Multiply that by the cost of transportation from A to D, which is $9. Add that with the flow times the cost from A to E. Add that with the flow times the cost from A to F, and do that for all the cells. So in this case, you have 12 total cells, and you have 12 combinations of costs and flows. So you're trying to minimize this sum. That is what you're trying to do. So the flow times the cost for every single cell that's given to you in that transportation grid. That is your objective function, to minimize this total cost. In terms of the constraints, if